Okay, continuing on with 3.1 and maybe do some of 3.2. Again, chapter 3 is our longest chapter. There's 11 sections. As you can see, it's going to be a while until we have the tests. Looking way ahead, the next test is not until what? Friday, October the 23rd. So that's quite a ways away. So the Fridays in between, there'll be quizzes. So quiz this Friday and Friday the 9th and Friday the 16th until Friday the 23rd, looks like. Okay. Or a little reminder, there's a flex day on Thursday, October 15th. There's no school for you all. Teachers have meetings, but you don't have to come that day. All right, so back to 3.1. So we're now doing derivative shortcuts. So now it's okay to do all the shortcuts that we talked about. Okay, so let's rehash some of them. All right, so derivative shortcuts. Most of the rest of the semester, you don't have to do limit h approaches 0, f of x plus h minus f of x all over h. You might need it again for the final, and very occasionally, perhaps from here on out. But most of the time, now you can do shortcuts. Okay, so derivative of a constant function is 0. Okay. The derivative of a power function, well, the derivative of x is 1. More generally, I showed you if you have mx, the derivative of mx is m. Okay, so if you have a linear function, then the coefficient is just the slope or derivative, since derivative means slope. So the derivative of 7x is 7. The derivative of negative 80x is negative 80. Okay, a big one was the power rule. Okay, the derivative of x to the n comes down, and then x to the n minus 1. That works for any real number n, although we haven't proven it. Actually, I haven't shown you proofs of hardly any of these. They are provable, but to save time under COVID, I'm holding off on a lot of proofs. Okay, but that n is allowed to be anything. Okay, any real number, positive, negative fractions, square roots, decimals, whatever. Okay, then power rule, we just did that. They're saying if n is any real number, so they didn't prove it. We might prove it on section 5 or 6 or something like that. Okay, constant multiplier rule. You give a constant times a function c times f of x. You can factor the c out and just take c times the derivative of f of x. Okay, so number times a function, just take the number times the derivative of the function. Okay. Sum rule. Derivative of a sum is the sum of the derivatives. You want the derivative of f of x plus g of x, just take the derivative of the first plus the derivative of the second. Same thing for a difference. Derivative of f of x minus g of x is derivative of f of x minus derivative of g of x. Okay. And exponential function, the derivative of e to the x is itself. Derivative of e to the x is e to the x. Okay. We'll learn the derivative of other bases like 2 to the x, 10 to the x. They're actually not as nice. Okay. But the derivative of e to the x is e to the x. Now, since I'm letting you have a cheat sheet, you can put all of these on a cheat sheet, but most of these so far should not be that hard to memorize. Okay, so we did a bunch yesterday, and I'll do a bunch more now. Okay, first thing I want to talk about is something called the second derivative. Okay, so what is the second derivative? Well, it's the derivative of a derivative. So when you have a function, right, you take a derivative, you get back another function. You can take a function derivative again. And some notation. Y with 2 apostrophes, right? So if this is y prime, we will say y double prime. So 2 marks, y double prime. F double prime of x. F double prime of x. Now what about the D notation, which I will now share with you? It's called the Leibniz notation, L-E-I-B-N-I-Z, Leibniz notation. So when you see the D notation, like a dy dx, it's called the Leibniz notation. Leibniz is one of the founders of calculus. He and Sir Isaac Newton are attributed to be the founders of calculus. Okay, second derivative. Okay, for first derivative, we have dy dx. second derivative, we now write something that kind of looks like d squared y over dx squared. That's how I'm going to say it, d squared y over dx squared, although you're not necessarily squaring anything. Okay, and that is correct. The 2 here is between the d and the y, but the 2 here is after the x. It's almost as if to say, if you're going to write it this weird, you must mean second derivative. Okay. After all, if I showed this to you in algebra, you might say, oh, maybe I'll cancel out the d's or something like that, right? Or maybe if you put the 2 over here, maybe I'll cancel out the d squared. So if you go out of your way to put this 2 superscript after the d, but put this 2 after the x, it's almost like, okay, that wasn't an accident. You have to mean second derivative. Okay, so Leibniz notation, the d notation, dy dx, or later ds dt, or dp dr. Okay, that is the so-called Leibniz notation for first derivative. And second derivative, we now say d squared y over dx squared. And yes, you've already heard me say this, but now that we have a second derivative, we will also say first derivative. Okay. Before, we didn't say first derivative. We just said derivative because it was the only thing in town. But now that there's a second derivative, we'll say first derivative, second derivative. It's kind of like where you have George the first and George the second, right? If there's only one George, you just say George. But if there's a second, now you can say, okay, George the first, George the second, George the third, or whatever, right? So before, we didn't say first derivative. We just said derivative. But now that we will have a second derivative, okay, we will now have occasion to say first derivative, second derivative. Okay, and I'll just go ahead and add, theoretically, you can have a third derivative, a fourth derivative. You can have as many derivatives as you want. Okay, for Calc 1, we almost never go beyond second derivative. Second derivative has some practical applications. Third derivative and higher, not for Calc 1. You will see higher derivatives in Calc 2. Okay, so Calc 2, you'll see third derivatives, fourth derivatives, hardly ever in Calc 1, but they exist. I mean, you can just keep taking derivatives of derivatives of derivatives of derivatives. So you can have second derivative, third derivative, fourth derivative, and so on. But for Calc 1, we usually don't go past second derivative. Okay, so they ask us for some second derivatives. So it's pretty easy. They give you a function, take a derivative, f prime, take a second derivative, that's f double prime. That's all. Okay, so for 47, find the second derivative. And by the way, in order to get the second derivative, you have to get the first derivative. So you can't jump straight to the second derivative in general. You have to get the first derivative, and once you get the second derivative, first derivative, then you do the second derivative. Okay, so the original function is 2x minus 5x to the 3/4. Get that yellow out. All right, so f prime, the derivative of 2x is 2. It's a linear function. What's the derivative of negative 5x to the 3/4? So we multiply, right? 5 times 3/4 is 15 over 4. X to the 3/4 minus 1 is negative 1/4, right? 3/4 minus 4/4. Okay, and then for the first derivative, we don't leave our answer like that, right? We're not supposed to have a negative exponent. So just drop that into the denominator. So our final answer for f prime, first derivative, is 2 minus 15 over 4x to the 1/4. Okay, but when it comes to taking the second derivative, I want to differentiate using this expression. Again, what does differentiate mean? It means taking the derivative. Right, so look at this. So f double prime, what is f double prime? It's the derivative of f prime. Or you can properly even say the derivative of the derivative is the second derivative. Okay, what's the derivative of 2? 0. It's a constant, so I don't have to write anything. And now I want to differentiate this thing, negative 15/4 x to the minus 1/4. All right, so now we know by the constant multiplier rule, it's negative 15/4 times the derivative of this. So negative 15/4 times negative 1/4 is a positive 15 over 16. X to the negative 1/4 minus 1 is negative 5/4. Okay, so calculus is done, and now for algebra, just bring that back into the denominator. So final answer, 15 over 16 x to the 5/4. Again, don't leave your answer with a negative exponent unless the problem started off with a negative exponent, right? If it started off with a negative, you can give your answer with a negative exponent. Okay, now for, let's see, I'm going to show you 49. Okay, so one application, and you physics people may have heard this already. All right, so they're talking about distance s. Okay, quite often we use s for distance, not d, because d stands for derivative. So we use s for distance, okay, and there's velocity and acceleration. Okay, so it turns out the derivative of distance is velocity. So velocity is the first derivative. Okay, acceleration will be the second derivative. Okay, and you physics people have probably heard that before, right? So distance function is s, first derivative velocity, second derivative acceleration. Okay. So s is t cubed minus 3t. Okay. So v, velocity, is s prime. A, acceleration, is s double prime. Okay, and let me talk quickly about the units. Okay, so if they have meters and second, so distance is in meters. Okay, velocity will be in meters per second. Or, yeah, meters per second. Or you can write SCC. Okay, acceleration is meters per second, or meters per second squared. Okay, so if we have meters and seconds, distance is in meters, velocity will be meters per second. I think you're comfortable with that. Acceleration will be meters per second squared, or feet per second squared, or whatever. So those are the proper units. Okay, again, you can put this in your cheat sheet if you want to, but it's not that hard to memorize, I think. Okay, so if you're given a distance function, s, not d, d stands for derivative, so s usually for distance. First derivative is velocity. Second derivative is acceleration, meters per second squared. Okay, so that's all. So they give me s is t cubed minus 3t. What's the velocity function? First derivative, s prime. So the derivative is 3t squared minus 3. The acceleration is the second derivative, the derivative of the derivative. So the derivative of this is 6t. The derivative of negative 3 is 0. So that's pretty much about it. Okay, and now you can answer any other questions about it. Okay, give the velocity and acceleration. So velocity is first derivative. Acceleration is second derivative. Acceleration after 2 seconds. So I plug in 2 to the second derivative. And then the acceleration when the velocity is 0. Okay, so that's a little bit more work. Let's get B out of the way. The acceleration after 2 seconds, I simply plug in 2 to the second derivative. It asks for the acceleration. So A of 2, 6 times 2 is 12 meters per second squared. Okay, and then C, okay, the C says, give me the acceleration. Oops, where'd it go? Give me the acceleration when the velocity is 0. Velocity is 0. Set the first derivative, velocity, to be 0. So I take my first derivative, there it is, s prime, or velocity, 3t squared minus 3, set it equal to 0. Okay, factor out the 3. 3 times t squared minus 1 equals 0. Factor 3 times t plus 1, t minus 1 equals 0. Okay, so t is equal to negative 1. Usually you throw out t is equal to negative 1. Usually when you have a science experiment, a science lab, when you press go, right, you start the experiment, t is 0. We don't normally start with negative. So, you know, you press your stopwatch, let's say, right? So time is 0. Okay, now it's 1 second, 2 seconds, 3 seconds, or whatever. You don't go to negative. So normally for situations like this, just throw out the negative. So all we have is t is equal to 1. Okay, so t equals 1 second. And they're asking for the acceleration when t is 1 second. So I just plug in 1 here. So the answer is 6 times 1, or 6 meters per second squared. Okay. So that's that. All right, so the key thing about this problem, right, so put this in your notes if you need to, but I don't think it's that hard to memorize. If you're given a distance function, first derivative is velocity, second derivative is acceleration. Okay. All right, so let's see. Let me try some problems toward the end. Let's see. So I've done what I want. So 45 to 61, right? We're more on these. Now, let me show you the Leibniz notation for 51. I wasn't going to do it, but it's not that hard. You have L as a function of A. So it's not Y and X. L is a function of A. So they say DL dA. See that? That's just like dy dx. So Y is a function of X. But they have L, length, as a function of age, A. Okay? So DL dA, and then they plug in whatever. Okay? It's not really any different. But you notice with the Leibniz notation, the D stuff, you know exactly what the variables are. The variables are L and A. You don't get that if you write Y prime or F prime of X. The two letters, the two variables are L and A. So that's all. It's not that big a deal. Okay, but I do want to show you some of these at the end. Let me show you 55. For what points on the curve Y equals blah, 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 where the tangent is horizontal? We'll have that theme quite a bit. Horizontal tangent. Now, if you have a horizontal line, what's the slope? Slope is 0. Okay. So horizontal tangent to the curve means slope is 0, derivative is 0. So I take the original function, horizontal tangent means I take the derivative, set it equal to 0. Okay. You don't really need a graph for it, but I'll make up a quick graph. So horizontal tangent might be something like this. Okay, slope is 0. Slope is 0. As you may notice, it looks like it might occur at a maximum point or a minimum point. We'll get to that much more in chapter 4. Okay, but slope is 0. Imagine this is a ride, roller coaster ride. Okay, we're always going from left to right. Okay. Here it looks like we would say we're going up, we're increasing. Right here at the top, slope is 0. And then I'm going down the roller coaster, and then slope is 0, and then I'm going back up or whatever. Okay, so this is a horizontal tangent. So this has a graph. We will learn how to graph these in chapter 4, but we're not worried about that right now. Okay, so I take the derivative and set it equal to 0. That's all. So what's the derivative of this? 6x squared plus 6x minus 12, and the derivative of 1 is 0. So there we go, right? So the sum and difference rule, if we want the derivative of the whole thing, I just take the derivative of this plus the derivative of this minus the derivative of this plus the derivative of this. So derivative of this, 6x squared, plus the derivative of this, 6x. And the derivative of negative 12x is negative 12. The derivative of 1 is 0. And there it is. So horizontal tangent means set this now equal to 0. Okay, so just do some algebra. Factor out the 6. X squared plus x minus 2 equals 0. Okay, leave the 6 alone. How do you get x squared? X times x. How do you get 2? 1 and 2. And you want to have a positive coefficient here. So the plus should go with a bigger number. So plus 2 minus 1. Okay, so by the 0 factor property, set each of these equal to 0. Well, you can't set 6 equal to 0. That's impossible. So forget about that. So what number makes this 0? 1. What number makes this 0? Negative 2. Okay. And then one last thing of which I won't do completely. The problem did say it wants points on the curve. That means x comma y. Right now we only have the two x values. How do I find y? Just plug in. Okay, so I want f of 1. So plug in 1 here, here, and here. So it's 2 times 1 cubed plus 3 times 1 squared minus 12 times 1 plus 1. 1 cubed is 1, 1 squared is 1. So I'm multiplying by 1, which means just forget about it. 2 plus 3 minus 12 plus 1 is negative 6. Okay, so the point on the graph is 1 comma negative 6. And I'll leave f of negative 2 to you. Okay, so you do that on your own. Okay, just plug in negative 2, negative 2, negative 2. And then your answer will be negative 2 comma blah, 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 blah. Okay. So that's that one. Okay, 57. Show that the curve, blah, 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 has no tangent line with slope 2. What does that mean? Okay, we know tangent means derivative. They're saying the derivative will never equal 2. Okay, so whatever this graph looks like, you're never going to have a slope with a tangent line of 2. Now, getting back to this thing that I just drew a moment ago, slope is 2. Okay, maybe somewhere like there. Maybe that's a slope of 2, rise over the run, right? Here it looks like the slope is negative and so on. So for this particular graph, okay, it looks like the slope can be 2. Here the slope is 0. Here the slope is negative something. I'm just making up stuff. -1, slope is 0, and so on, right? On a roller coaster ride, the slope keeps changing as you go up and down and so on. But for this particular one, they're trying to say there is no place where the tangent has a slope of 2. Okay, so how do I do that? Okay, so first let's take the derivative. Okay, what's the derivative of 2e to the x? 2e to the x. Okay, so this is a constant times a function. The derivative is the constant, 2, times the derivative of the function. The derivative of e to the x is itself, e to the x. So 2e to the x. And what's the derivative of 3x? 3. And what's the root of 5x cubed? 3 times 5 is 15, x squared. All right, and here's the key thing for this. I claim this thing is always going to be greater than 3. Okay, we have 3. Look at 15x squared. What can we say about 15x squared? It's never going to be negative. The smallest this can ever be is 0. That's if I plug in 0. Right? So right now, if I only look at this, 3 plus 15x squared, it's 3 at a minimum. Right? Now, do you remember something about e to the x? E to anything is always positive. And then if you multiply by 2, it's definitely positive. Right? So I've got a positive plus 3 plus a non-negative, which means 0 or higher. That definitely has to be bigger than 3. So all 3 of these combined have to be greater than 3. Here's 3. This isn't negative. This isn't negative. So it's only going to get bigger. So I've shown you the slope can never be 2. Okay, so that's all. Slope can never be 2. All right, then 61, and then I'll get started with sum of 3.2. Find the equation of the normal line to the curve y equals square root of x that is parallel to the line 2x plus y equals 1. Okay, what is a normal line? The normal line is perpendicular to the tangent line. Okay. So if I go back to this picture here, okay, here's a tangent line, right? If I draw something like so, where this is a 90-degree angle, this is a normal line. And this is a tangent line. Okay, so the normal line is perpendicular to the tangent line. Okay. Normal line is perpendicular to the tangent line. And in particular, it's at this point where they're tangent. So the language we would say is at the point of tangency. Okay, so here's a normal line. Here's a normal line. Here's a normal line. Where these are all right angles. I'm trying to draw a little right angle there. Okay. So you know the tangent line just grazes the graph. You have a normal line. Just make it perpendicular at the point of tangency. So, you know, I could make it perpendicular here or way out here, but it's at the point where they're tangent. So that's what we say. The normal line is perpendicular to the tangent at the point of tangency. Okay. I didn't write the word line here, but that's okay. The tangent is often okay to say the tangent line. tangent does mean a tangent line. Okay, so how do I do this problem now? So y equals square root of x. You want the normal line that's parallel to this. So what's the slope of this line? 2x plus y equals 1. Move over the 2x. Y equals negative 2x plus 1. So the slope of this line is negative 2. All right, now the slope that I want, okay, the normal line, if it's going to be perpendicular, do you recall what happens for perpendicular lines? I take the negative reciprocal of negative 2. Right? Two lines are perpendicular if the product of the slopes is negative 1, or another way of saying it is if one slope is the negative reciprocal of the other. So what's the negative reciprocal of negative 2? Positive 1/2. So this says m wanted, the m that I want, is the negative reciprocal of negative 2. That means flip and change the sign. If I only ask for reciprocal, you would say negative 1/2, but take off the negative also. So the m that I want is positive 1/2. All right, so where on the graph is the slope 1/2? All right, so first I find the derivative. So y equals x to the 1/2 power, right? Square root of x is x to the 1/2. X to the 1/2. So dy dx, what's dy dx? Derivative. So I'll be writing them all. I'll write dy dx, f prime, y prime. Okay, so 1/2 x to the negative 1/2. And then better for algebra is 1 over 2 radical x. Okay, x to the negative 1/2 means put a square root on the bottom. Now I set it equal to 1/2. I'm trying to find out where is the slope 1/2. So 1 over 2 radical x equals 1 over 2. You can cross multiply. Remember cross multiply? That times that is equal to that times that. So 2 equals 2 radical x. Divide by 2. 1 equals square root of x. Square both sides, and x equals 1. And if you plug in 1, you get y equals 1. All right, so what point are we at? 1, 1. So there it is. Okay, so this problem's done. I'll dig a little bit deeper, just for fun. So very crudely, y equals square root of x looks like this. This is the point 1, 1, right? The tangent to the curve right here is 1/2, which means the normal has a slope of negative 2. All right, so all of these are going on at the same time. Y equals square root of x looks something like this. The slope of this tangent line is 1/2. The slope of the normal line is negative 2. All right. All right, that was it that I was going to show you for 3.1. I might come back and do some more problems, but I wanted to introduce 3.2 now. Okay, so starting 3.2 is on the product and quotient rules. Product and quotient rules. All right. The first thing I'm going to say about the product rule and quotient rules are, in order to prove it, I'll just show it to you quickly. If we were meeting face-to-face, I'd show it to you more, but I'm not going to. But notice you use the limit definition. If you want f of x, g of x, a product, something times something, f of x, g of x prime, notice what I did, right? Limit h approaches 0, f of x plus h, g of x plus h, minus f of x, g of x all over h. Okay, have you run through this whole thing? Okay, I'm just going to show it to you in case somebody is curious, how do we actually prove it? Okay, so this is recorded, so I'll show you this. Here's the proof of the product rule. So I'll just show it to you in case you want to look at it sometime. I'm not testing you on any of this, by the way, but here we go. All right, but I'm just going to say quickly about the product rule. It's not as easy as take the derivative of the first times the derivative of the second. Okay? Your intuition. Okay, remember for a sum, f plus g, just say, oh yeah, take the derivative of the first plus the derivative of the second. That's true for a difference also. F minus G, just take F prime minus G prime. Doesn't work that way for products. It also doesn't work that way for quotients. Okay, so watch out for that. So what is the product rule? Okay, so here's the proof of it. Here's the final result. Okay, if you want to put this in your cheat sheet, you may. If we were meeting face to face, I'd make you memorize it. Okay, but FG prime plus GF prime. Okay, so this is called the product rule. Product means multiply. FG prime plus GF prime. In words, first function times the derivative of the second function plus the other way around. Second function times the derivative of the first. Okay. So don't go F prime times G prime. That would be a good guess. That would have been my first guess when I first learned calculus. I would think, oh, if I want the derivative of something times something, I'd just take the derivative of the first times the derivative of the second. No, doesn't work in general. Okay, so FG prime plus GF prime. Now, there are other ways you could write this. Okay, I'm asking you to please do it this way. Again, not because what you have might be wrong, but I only want to look at one thing. When I'm grading all your papers, all your homework, all your quizzes, all your exams, there are 43 of you. It's a lot easier if all of you do the same thing. Okay, so you could say, yes, you could theoretically switch this around and switch this around and move that over there. Addition is commutative. Multiplication is commutative. Okay, so in theory, you could switch all this around. I don't want you to. Please just do it exactly like this, so it's easier for me to grade. Okay, am I going to take off points if I get it some other way? Maybe. Okay. If you do it like this, I will not take off points. That's, maybe that's the best way I can say it. If you change the order, you're tempting me. Put it that way. You're tempting me to take off points. Okay. If you do it like this, FG prime plus GF prime, I definitely will not take off points. That's what I'm looking for. If you put the F after the G, or if you put the G after the F, or if you put that in front of that, or if you put the prime in front of there, you're making it harder for me. So if you're making it harder for me, I might want to take off points, put it that way. Okay. So if you do it exactly like this, I will not take off points. If you don't do it like this, then all bets are off. Okay, I might take off points, I might not. But you really, just for my sake, so I can grade 43 of you all the same way, it's easier if everybody does it this way. First times the derivative of the second, plus the second times the derivative of the first. Okay, first example, 3.2, number 3. F of x equals 3x squared minus 5x times e to the x. Okay, so this is my first function. This is my second function. All right, so f prime, fg prime plus gf prime. First times derivative of the second, plus the second times derivative of the first. By the way, that's a plus symbol right there. So I copy the first function, 3x squared minus 5x. Be careful, don't take the derivative of the first function here. Just copy the first function, and then times the derivative of the second. So what's the derivative of e to the x? Itself, e to the x. Plus second function, copy it, e to the x, times the derivative of the first. So now I differentiate the first, which is 6x minus 5. Okay, that's essentially it, but to clean it up, I factor out the e to the x. See how there's an e to the x in common here and here? So I factor out e to the x. I'm going to have 3x squared minus 5x plus 6x minus 5. Okay, and then I said to myself, wait a minute, I have minus 5x and plus 6x. Might as well just write it as x. So the best final answer is 3x squared plus x minus 5 times e to the x. Okay. So this is the product rule. Okay, I just made this one up for practice. It's not necessarily any question, but d dx of x e to the x. Again, don't get scared by the notation. It's just saying, give me the derivative. Okay, or pretend it said y equals x e to the x. I'll be finding dy dx. Well, here's why. So the derivative of x e to the x dx. Okay, so first function, second function. So the way it goes again is first times the derivative of the second plus the other way around. Second times the derivative of the first. So first function is x times the derivative of the second. So what's the derivative of e to the x? Itself, e to the x. Plus second function times the derivative of the first. What's the derivative of x? It's 1, so it's e to the x times 1, which means you don't have to write it if you don't want to. Okay, so that's the answer. Or again, you can factor out the e to the x. So I take out e to the x, then have x plus 1. So x plus 1 e to the x is the best final answer in this particular case. Okay. All right, so this is the product rule. And I will show you also the quotient rule. Here's the derivation. What's the derivative of f over g? Okay. Again, it's not as easy as taking f prime divided by g prime. It doesn't work that way. Here's a derivation if you want to look at it. You don't have to look at it. I'm not testing you on it. But in case you're curious, use the limit definition, right? Limit h approaches 0, f of x plus h over g of x plus h minus f of x all over g of x divided by h. Okay, there's this big, long mess for the derivation. So we're being recorded. So if you absolutely just got to see where this rule comes from, okay? So here it is. Here's some more derivation. But here's what you end up with. Okay, g of x, f prime of x minus f of x, g prime of x all over g of x squared. Okay, making it more compact. So here we are, f over g prime. Here's the proof. You don't have to look at the proof if you don't want to. I'm not testing you on the proof. But somebody here might say, where did that rule come from? Here's where it came from. Okay, you can derive the rule by using definition. All right, more compact. F over g prime. G f prime minus f g prime all over g squared. Okay. In words, bottom times the derivative of the top, g f prime, minus the other way around. So that was kind of like the product rule, where you do one thing, you have one function times the derivative of the other, and then you switch it around. Okay. One big difference, though, for the product rule, there was a plus. For the quotient rule, it's a minus. So it's minus the other way around. So bottom times the derivative of the top minus the other way around. Top f times the derivative of the bottom all over the bottom squared, all over g squared. So this is the quotient rule. Again, if we were meeting face to face, I'd make you guys memorize it. But since we're in the COVID, I'm letting you have a cheat sheet. Okay? So g f prime minus f g prime all over g squared. Okay. Now, you actually have less variability here. Okay. So this time, especially since there's a minus, you cannot turn the 2 around because you would actually be getting something different. Okay. So unlike the product rule, where you've got a lot of play here, you can turn this around, you can turn this around, you can turn this around, but not this one. Since it's a plus, you can put this whole thing in front of that. Okay. There's a lot of ways you can do that. Less variety for this. But again, to make it easier on me, I would like everybody to do the same thing. G f prime minus f g prime all over g squared. If you do it like this, I will not take off points. If you give me something equivalent, but it doesn't look like this, I'm not going to say. I might take off points, I might not. So, but if you always do this, that's what I want. That's what I want to see for the majority of you, for all 43 of you. Then I will not take off points if you do it this way. Okay. So g f prime, bottom times the derivative of the top, minus the other way around, f g prime, top times the derivative of the bottom, all over g squared. Okay. I'm going to say something quickly in terms of algebra. This will always match this. It's the bottom. This is the square of the bottom. You might want to cancel this with this. You're not allowed to because of that minus sign, right? You might recall if you have a subtraction, you're not allowed to cancel. The only way you can cancel here is if this came out to be 0 somehow. Okay, so if the fg prime came out to be 0, then you can cancel the g's. Right? Or maybe you can factor out somehow a g and then partially cancel here. But otherwise, you're not able to. Okay. Number 9, let me show you number 9. Number 9, there's a certain way to do that one. Oh, there's an easy way and there's a hard way. Question number 9. U minus radical U, U plus radical U. Now, the hard way is to use the product rule. Can you see what would be a much easier way? Especially they write it like that, U minus radical U, U plus radical U. Just multiply it out. These are conjugates already. So it's of the form A minus B, A plus B. That's going to be A squared minus B squared. And I like that because what's the square root of U squared? That's just going to be U. Right? That comes out very nice. Okay. So I messed up here. This is U minus radical U, U plus radical U. That's like A minus B, A plus B. So I square U, U squared, and then I square radical U. What's radical U squared, or radical U times radical U? U. So U squared minus U. So this one I highly recommend against doing the product rule. Right? You got to change that to U to the 1/2. The derivative is 1/2, U to the minus 1/2. You don't want to fool with that. Just make it U squared minus U. And now H prime is simple, 2U minus 1. Okay. So that's pretty straightforward, I hope. All right, show you one example of the quotient rule, and then maybe I'll stop after that and take some questions if you have any. Okay, number 7. G of x is 1 plus 2x over 3 minus 4x. Okay, so here's our first example of the quotient rule. F over G. So bottom times the derivative of the top minus the other way around. Top times the derivative of the bottom all over the bottom squared. Okay, so G prime of x, bottom, 3 minus 4x, times the derivative of the top. So what's the derivative of 1 plus 2x? 2. Derivative of 1 is 0. Derivative of 2x is 2. Minus, okay, I know it looks like a plus, but that's because there's a double negative here. There's a minus here. Minus the top, 1 plus 2x, times the derivative of the bottom. So what's the derivative of the whole bottom? Negative 4. The derivative of 3 is 0. The derivative of negative 4x is negative 4. Okay, so there's a negative here and a negative here, which means I'm immediately changing them to pluses. That's what I did over there. That's all. Okay, normally I don't bother multiplying out the bottom, but it is worth it to multiply out the top because we're going to see a cancellation. And by the way, that's a recurring theme of a lot of this. That theme occurred when we were doing the derivatives by the definition, right? We said work out the top but not the bottom. Okay, so distribute the 2, that's 6 minus 8x. Distribute the 4 plus 4 plus 8x. 2 times 3, 6. 2 times negative 4x, 8x. 4 times 1, 4. 4 times 2x, 8x. And notice very conveniently the cancellation, right? 8x is cancel out. So final answer is 10 over 3 minus 4x quantity squared. And you should do this because you can see this is a lot nicer than all that stuff, right? I mean, which is easier? We're talking about simplification. Is this numerator simpler or 10, right? 10's a lot easier. So that's why you should simplify if possible. Okay. All right, so I was going to stop there. And so let me stop the share. And let me check the chat unless Prasanna already got it. Okay, so. So Prasanna, you got that? Okay. Thank you, Prasanna. 3.157, what is the subscript you had? Yeah, it was M wanted, W-A-N-T-E-D. It was the M wanted there. Okay. All right, let's see. 3.131. Let me see if I can do that quickly. Almost out of time. Remember, these might be pretty fast. 3.131. Okay, we might be able to just knock that off real quickly, and then that's about it. 3.131. Z is equal to A over y to the 10 plus B e to the y. Okay. Okay. Now, what does it want to mean? That's the slope that we want. Okay. We didn't want to use the original slope. We had to get the negative reciprocal. You might recall. So that's the slope that we want. Okay, let's see. Gotta push the right buttons here. All right, for this one, A is a constant, B is a constant. The only real variable is y. So treat A as a constant. So Z is A, y to the negative 10th plus B e to the y. So using the Leibniz notation, dz dy, rate of change of z with respect to y. Remember, A is a constant. So negative 10 hits the constant. So negative 10 A y to the negative 11, negative 10 minus 1. Okay, and how do I differentiate this? And so what does differentiate? It means take a derivative. So constant times e to the y. The derivative is the constant times the derivative e to the y, which is itself. So b e to the y. Last thing is to draw the y to the negative 11 back downstairs. So final answer is negative 10a over y to the 11 plus b e to the y. Final answer. Okay. All right, and that's pretty much about it. And yes, thank you, Prasanna. Anytime anybody wants to ask a question in the chat while I'm blabbing away, you can ask Prasanna something, and Prasanna will be glad to help in that situation also. Okay. All right, I see it's just about 1 o'clock, folks, so that'll do it for today. All right, so have a good day, everybody. See you tomorrow. Bye.